the total resistance by three conductors, the resistance R1, R2, R3, connected in parallel, is given as follows. How can we find the partial derivative of the total resistance with respect to the resistance in the first conductor? First off, I would like to acknowledge all the electrical engineering majors for watching this video. I don't think there are too many. I honestly don't like this. I don't like it. You had to study it before. Not my thing, you know. Nevertheless, here this is one of the questions where you have to think about the right object. If you use the right object for this, then solving this exercise will be very simple. Let me make my words precise. We are right now talking about partial R1. This is a value we would like to find. And I claim that the key is to define a function f which will be equal to 1 over r. This is a function of r, correct? But notice that at the same time, 1 over r is equal to 1 over r1 plus 1 over r2 plus 1 over r3. Which means that in a sense, f of r is equal to f of r1, r2, r3. Not equal in that sense. You cannot just take any arbitrary function of r and then say it's function of r1, r2, and r3. It just works for our example here. To be precise, we're saying that this function which we've written to have a dependency on r also has dependency, or maybe alternatively has dependency on r1, r2, and r3. And this will be useful because we will be computing some partial derivatives. We're looking to find partial derivatives of r in r1. Maybe it's a good idea to explore how that would be like. So now I will take not the partial derivative, but the total derivative of f. And the total derivative is just the normal derivative that we have. The derivative of this function 1 over r is minus 1 over r squared. I don't think that's too difficult. At the same time, I would like you to notice that we can take the partial derivative with respect to r1 of this function. And that would give us minus 1 over r1 squared. Why is that? Simply because we consider this equivalent expression. And for this equivalent expression, we take the partial derivative of f with respect to r1. If we're taking that with respect to r1, then r2 and r3 are treated as constants. In other words, these do not change with respect to r1, and so they are neglected. That is good. Now here's what we need to do. We need to compose these two somehow and get this final result. I see that partial r1 is it's in the bottom, so maybe we'll keep it like that. And maybe we'll flip the other one. So in other words, this would imply that the rate of change of r with respect to f is equal to minus r squared. Now we cannot do the same thing here because this is a partial derivative and not a total derivative. So this is a common mistake. You can check yourself that this is not equal to partial r1 partial f. Here it works because this is the only input we have. I mean, this is the only input. We only have one variable, and we know this from calculus 1. But in the case of the partial derivative, this is not. It generally does not work. So be careful. Now that we have this, I claim that dr by df times partial f divided by partial r1 gives us partial r times partial r1, which is going to be equal to minus r squared times minus 1 over r squared, well, r1 squared. The minuses cancel out, and we get the following as the answer. Now perhaps this requires some justification. Maybe I need to say a few words on why this works. And the simple reason why this works is because these two are equal. The partial derivative of a function in one variable with respect to that variable is just a total derivative because there's only one variable. And since this is a total derivative at the same time, we can flip it in the sense. That's the only reason we can flip it. And the only reason why it works. So this is a little bit of trickery, if you think about it. Perhaps it is a better idea to write this as the partial derivative version. Then it makes perfect sense. That's all I have to say.